Text embeddings are essential for many natural language processing tasks, such as document retrieval, textual similarity, or question answering. However, previous text embeddings often focus on a single task, limiting their ability to generalize. For example, SimCSE is great for text similarity tasks, but it's not very effective for text retrieval. On the other hand, models trained for document retrieval struggles with text similarity tasks. In recent years, researchers have been trying to create multitask embedders by training a single model on several task-specific datasets using instructions. Instructor is a representative example. Alongside these developments, massive text embedding benchmarks have emerged to systematically evaluate text representation models on a large amount of tasks and datasets. However, existing methods still have a few limitations. They either rely heavily on in-house training data, or they require human-engineered prompts tailored to each task, which increases the complexity and labor involved in training. With that in mind, the paper proposed the following question. Is there a straightforward approach to build a general-purpose text embedding model only using open-source dataset without heavily relying on manually annotated or prompt-engineered dataset? To begin with, let's first look at the architectural design of GTE. The model doesn't use a complex structure. It sticks to a simple vanilla dual encoder architecture. Given a piece of text with tokens x1 to xn, they first obtain contextual representations from a language model, such as BERT, and then apply a min pooling across these token representations to form the text embedding. What really stands out in GTE is the process of gathering pre-training data. For unsupervised pre-training, they gather large-scale text data from the web, about 800 million text pairs, without needing manual annotations. Although there are slight differences between sources, they generally gathered text pairs by using the title of the source as the query and the main content as the document. The issue is that the data sources often differ significantly in terms of the number of the training instances. To handle the imbalance across different data sources, they use the multinomial sampling. Each dataset di is sampled with probability of the given formula, where alpha equals 0.5. This helps the model to avoid biases toward any particular dataset. Another interesting point of GTE is the improved contrastive loss that expands negative samples in a bidirectional manner. Traditional info and CA loss compares each query to in-batch positive and negative documents. Since it focuses on each query and compares its relationship with documents, it can be considered a unidirectional training approach. However, the improved contrastive loss not only compare each query to in-batch documents, but also compare queries to other queries and documents to other documents. This approach effectively increases the number of negative samples within a fixed batch size. And this extended set of negatives tightens the decision boundary between texts that should be similar and those that should not. Even with this improved contrastive loss, having a large batch size still plays a crucial role in improving training performance. It helps the model see more negative examples in each iteration, reducing the gap between training and inference while providing a better approximation to the underlying contrastive learning objective. In this paper, about 16,000 batch size is used for the pre-training. Now, let's see how the unsupervised pre-trained model performs in text retrieval. Remarkably, it outperforms BM25 on the BEER benchmark using only unlabeled datasets. Also, as you can see in the table, It beats previous state-of-the-art unsupervised models such as Contrastive or E5. This strong performance stems from training on a diverse range of data and incorporating various self-supervision signals. The authors even fine-tuned this pre-trained model on well-known labeled datasets such as MS Marco and natural questions. These datasets help the model learn specific tasks, further enhancing its performance. When looking at the MTEB benchmark, the supervised fine-tuned GTE-based model with 110 million parameters even surpasses a model 10 times larger, Instructor XL, showing that a well-trained, smaller model can outperform bigger models lacking robust training strategies. To understand why GTE performs so well, we'll look at two critical factors: diverse data sources and large batch size. As you can see in Figure A, introducing more diverse data consistently boosts performance, especially in pre-training stage. The graph shows the performance at each level of the pre-training stage when using 5, 15, and 33 datasets. This corroborates the idea that variety in training data helps generalize better. Figure B demonstrates the importance of large batch sizes for the contrastive objective on pre-training. When more negatives per batch, the model can capture subtle differences between text samples more effectively. The table shows the effect of improved contrastive loss. In both pre-training and fine-tuning steps, the improved objective provides consistent performance gains compared to vanilla info and CE loss. This implies that the improved contrastive loss function efficiently expands the negative pool even in a fixed batch size scenario. This paper demonstrates that it's possible to build a general text embedding model using a very straightforward approach: contrastive learning on massive open source data, followed by targeted fine-tuning on standard supervised dataset. That's it for today, and thank you for watching. Happy New Year, and see you in the next video. Bye.